What specific problem does your proposed method or algorithm aim to solve in the context of graph learning?
The proposed method aims to address the shortcomings in current graph learning benchmarks, particularly the lack of transformative real-world applications and the inadequate construction of graph datasets. It emphasizes the need for a shift from narrow, less relevant 2D molecular benchmarks to more meaningful problems that can be naturally represented as graphs, such as combinatorial optimization and other high-potential areas like social networks and automated chip design. Additionally, the method advocates for the development of robust evaluation frameworks and standardized benchmarking practices to ensure fair comparisons and reliable performance assessments across different models. By focusing on these aspects, the proposed approach seeks to create a foundation for scalable and impactful graph learning that aligns with real-world applications. Ultimately, it aims to facilitate the emergence of true foundation models for graph data, enhancing the overall effectiveness and relevance of graph learning in various domains.
How does the proposed method or algorithm work? Illustrate step by step, including all theoretical underpinnings and novel components introduced.
The proposed method utilizes a multitask pre-training and fine-tuning framework based on an encoder-processor-decoder architecture. Initially, the model is pre-trained on a diverse upstream mix of datasets, including PCQM4MV2, COCO-SP, and MAL and ETTINY, which vary in application domain and graph characteristics. During this phase, both a message-passing neural network, MPNN, and a graph transformer, GT, are trained to learn general graph representations, with the processor network being evaluated against an empty graph baseline to assess the importance of graph structure. Following pre-training, the model is fine-tuned on a downstream mix of datasets, such as Pascal-Voc SP and peptide struct, to evaluate its transferability and sample efficiency. The results indicate that pre-training enhances performance, particularly in scenarios with limited optimization steps, demonstrating the model's ability to learn useful representations across different tasks and domains.
Can you provide a straightforward example that illustrates the inner workings of your proposed algorithm? Please walk through the main steps with this example.
In our proposed algorithm, we utilize a multitask pre-training and fine-tuning framework based on an encoder-processor-decoder architecture. For instance, consider a scenario where we aim to predict molecular properties using a dataset like PCQM4MV2. First, we pre-train a general-purpose processor network on a diverse upstream mix of datasets, including PCQM4MV2, COCO-SP, and MAL and ETTINY, which vary in application domain and graph characteristics. During this pre-training phase, both a message-passing neural network, MPNN, and a graph transformer, GT, learn to extract useful representations from the graph structures present in these datasets. Next, we fine-tune the pre-trained models on a downstream mix of tasks, such as predicting properties in the Pascal-Voc SP dataset. Here, we measure the performance of the pre-trained models against single-task baselines to evaluate their sample efficiency. The results indicate that the pre-trained models often outperform their single-task counterparts, demonstrating their ability to transfer learned representations effectively across different tasks. This example illustrates how our algorithm leverages multitask learning to enhance performance in graph-based predictions.
What are the theoretical or practical benefits of using your proposed method compared to existing alternatives in graph learning?
The proposed method emphasizes a multitask pre-training fine-tuning framework using an encoder-processor-decoder architecture, which offers several theoretical and practical benefits over existing alternatives in graph learning. Firstly, this approach allows for the learning of general graph representations that can be beneficial across diverse tasks, enhancing model performance in both in-domain and cross-domain scenarios, as evidenced by improved results on datasets like Pascal-Voc SP and Stargazers. Secondly, by integrating various graph tasks during pre-training, the method promotes sample efficiency, particularly in scenarios with limited fine-tuning steps, which is crucial for real-world applications where data may be scarce. Additionally, the framework's design facilitates the exploration of different graph structures and tasks, potentially leading to the development of more robust foundation models for graph learning. Lastly, the proposed method addresses the limitations of existing benchmarks by advocating for a systematic evaluation of model performance across diverse datasets, thereby fostering a more rigorous benchmarking culture in the graph learning community.
How is your method validated or tested? Describe the experimental design, datasets used, and metrics for performance evaluation.
Our method is validated through a series of experiments involving multitask pre-training and fine-tuning using an encoder-processor-decoder framework. We utilize diverse datasets for both upstream and downstream tasks, including PCQM4MV2, CocoSP, and MALNETTINY for pre-training, and PascalVoc-SP, peptide struct, and stargazers for fine-tuning. The experimental design assesses the performance of our models against an empty graph baseline and their single-task counterparts, measuring performance across various optimization steps to evaluate sample efficiency. We report metrics such as mean absolute error, MAE, and performance improvements relative to baseline models, highlighting the effectiveness of our approach in transferring learned representations across different tasks. The results indicate that our models can learn general-purpose graph representations, demonstrating their utility in both in-domain and cross-domain applications.
What specific results were achieved with your new method, and what do these results signify for the field of graph learning?
In our experiments, we observed that both the message-passing neural network, MPNN, and graph transformer, GT models demonstrated non-trivial performance improvements compared to an empty graph baseline, indicating their ability to learn general graph representations useful across multiple tasks. Specifically, while both models fell short of their single-task baselines on CocoSP and PCQM4MV2, they outperformed their single-task counterparts on the MALNETTINY dataset when trained in a multitask setting. This suggests that our proposed multitask pre-training fine-tuning framework can enhance model performance, particularly in scenarios with limited data. Furthermore, we found that pre-training generally improved sample efficiency, especially in the fewest optimization steps, highlighting the potential for better transfer learning in graph-based tasks. Overall, these results signify a promising direction for advancing graph learning by leveraging multitask learning strategies to develop more robust and generalizable models.